Another common way of carrying out processes in the laboratory is adiabatically. Let's look at what happens during an adiabatic expansion of a gas. When we allow our gas to expand adiabatically, we make sure that no energy as heat enters or leaves the system. So we have an adiabatic wall around our piston, and Q is equal to 0. However, because we have expanded the gas, our work is negative because we have transferred energy as work to the surroundings. When we transfer that energy as work to the surroundings, our system now has less energy and thus populates less microstates, and the temperature is going to decrease. We can calculate this final temperature if we know the initial temperature and the change in volume, or the initial and final volumes. We'll do this by utilizing the first law of thermodynamics. In this adiabatic expansion or compression of a gas, dq is going to be equal to 0. Since dq is equal to 0, dE is equal to dW. When we have an ideal gas, the energy is a function of the temperature only, and so dE can be expressed as C sub V dt. dW, we know, is equal to minus P dV. If we know the equation of state, we can plug in for the pressure, separate variables, and integrate to get an expression for the temperature, initial and final, as a function of the initial and final volume. For an ideal gas, the pressure is nRT over V. Making that substitution and dividing through by T to get all the temperatures over here and all the volumes over here, we can integrate both sides of this equation, do some algebra rearrange, and show that the final temperature is related to the initial temperature by the ratio in volumes raised to the gas constant divided by the heat capacity at constant volume. During an expansion, the final volume is larger than the initial volume, making this ratio less than 1. Thus, the final temperature will be lower than the initial temperature as we initially reasoned out. However, if we are compressing the gas, the final volume will be smaller than the initial volume, making this ratio greater than 1, and the final temperature larger than the initial temperature. And so, in an adiabatic expansion, the gas cools, and in an adiabatic compression, the gas heats up. Again, our mathematical expression only tells us what we can reason out by thinking about the amount of energy in the system. When we expand the gas, energy leaves the system as work, leaving less energy in the system and a lower final temperature. When we compress the system, we add energy as work, and therefore the energy in the system increases and the final temperature should be larger.